Let's now take a look at the next section of our Science 10 chemistry review. So again, we're going to look at what do you remember from chemistry from Science 10, and the next section we're going to look at is classifying compounds. So how do we classify compounds? Essentially, we classify them either using our words ionic or molecular. Now, a few things to remember. Ionic compounds are compounds that, and I'll just write this down here, ionic equals they have or consist of a cation and an anion. All right, so the cation is your positive ion and your anion is your negative ion. All right, molecular compounds, however, they consist of two or more nonmetals. Now that's important. Sometimes we generalize and say that ionic compounds consist of a metal and a nonmetal, and molecular is two nonmetals. However, I prefer to say that ionic compounds are a cation and an anion because that is a little bit more specific to allow us to incorporate polyatomic ions in there as well. So we have to remember how to name ionic compounds and how to go from a chemical symbol to a name. So we have to go back and forth between those. Same with molecular compounds. So when we're going to name ionic compounds, we're going to take a look at a few different examples here. But there's a few things you need to keep in mind. We have to keep in mind if we're looking at a polyatomic ion. We have to keep in mind if we're looking at a multivalent element, meaning that there's more than one charge that we can be dealing with that element. And we have to keep in mind also that we must have our cation first and then our anion in both the symbol and the name. So if we start out with a few things, like let's look at, what's a good example? We'll go with iron 3 bromide. Now, one thing you want to note is that it's not iron 3 bromine, it's IDE. We always end our compounds with an IDE, so we change that nonmetal to have an IDE ending. Okay, so if we look at iron 3 bromide, we know that it has iron in it, and the charge that we have on iron is Fe3 positive. We're mixing that with our bromine, and our bromine has a 1 negative charge. So for every 1 iron that has a 3 positive charge, we know that ionic compounds do not have a net charge. So if this has a 3 positive charge, I have to have 3 negatives, which means I need 3 whole bromines to cancel out my 3 positive on my iron. So I need to have 1 iron with a 3 positive charge and 3 bromines. So I crisscross my numbers. So this is a 3 and this is an invisible 1. And I crisscross those down. So I get FeBr3. Okay, so that's iron 3 bromide. Let's take a look at another example. What if I have, what's a good example? Let's go with iron. This time we'll go with iron 2. And we'll say iron 2 phosphate. Oops. Iron 2 phosphate. So I know that my iron has a 2 positive charge because it's indicated by the Roman numerals, so iron 2. And when I look at phosphate, I notice that it doesn't have an IDE ending, which indicates to me that it's a polyatomic ion. So when I jump over to my polyatomic ions on my periodic table, or my data booklet here, okay, so here's my periodic table. If I zoom into my polyatomic ions, I'll let that get a little clearer. And I look for phosphate. So once I find phosphate on my table of polyatomic ions, I see that it's PO4 3-. So if I jump back over to my lesson, I know that it's PO4 3-. Okay, so now again, I just crisscross my charges. For every 2 positives, I need to have 2 negatives. But because I have an even number and an odd number, I have to have 3 irons with a 2 positive charge, resulting in a positive 6 charge overall. And I need to have 2 phosphates times the 3 negative charge to get a negative 6 charge overall. So again, I call it crisscross applesauce. I crisscross my charges down, and I would get Fe3, meaning that I need 3 iron atoms for every 2 phosphates. So one thing you need to keep in mind is I'm talking about phosphate as a whole little almost mini compound. I need to have 2 of those entire things. So I have to make sure that I put that in brackets again so that I'm not saying PO4 2, because that would be 1 phosphorus and 42 oxygens. I need to ensure that I put a 2 outside of the brackets there to indicate that this is 2 phosphates, 3 irons. Okay, another example I could take a look at would be something like manganese. Actually, let's use a different example. I'm going to say calcium calcium oxide. Okay, if I look at calcium oxide, I know calcium has a 2 positive charge. Okay, if you're unsure, you can flip back to your periodic table and take a look. Oxide has a 2 minus charge. So when I create that, you would expect to get Ca2 because you crisscross your charges, okay, and O2. However, because I really only need 1 oxygen to cancel out my calcium, because I have 2 positive charge, so I need to cancel out my 2 positive with a 2 negative, which just means I need 1 of each. So because I only need 1 of each, it's just CaO as my compound. So I don't need to get too crazy. I just need to crisscross my charges and then reduce to the lowest common denominator, lowest common coefficient. So when I do that, I see that it's 1 and 1. So we're good. Okay, I can take a look at one more example where I might need to do that. And let's look at manganese 4. Let's go with sulfide. So manganese 4 means that it's manganese with a 4 positive charge, and sulfide has a 2 minus charge. So again, when I crisscross my charges, I would expect to get Mn2S4, but because I can reduce those, I can get MnS2. Again, I reduced it. I would have had an Mn2S4, but because I can divide both of those by 2, that is my simplest way to write that ionic compound. Now, if we go the other way, if I take a look at a different example, and I'm given, let's take a look at this example. Oops. Let's put a little line in the middle. We're looking at a different example here. Lead bromide. Okay, so when I take a look at lead bromide, okay, I'm going to say that I know that it's lead, and I know that it's either Pb, and let's just go and jump back to our data booklet, our periodic table. Let's find lead here. And when I zoom into lead, I see that it's a 2 positive or a 4 positive charge. So when I jump back, I'm just going to write that down. I know, oopsies, I know that it can be a 2 positive or a 4 positive charge. Okay, I also know that I have bromine, which is a 1 minus charge. Now, because when I needed 2 bromines for every 1 lead that I had, I know that I was given a charge on my lead being lead 2 positive, because I needed 2 bromines to cancel out those 2 positive charge. So I would call this then, I would go in reverse and call this lead, and in Roman numerals, I'd identify which charge I used. So lead 2 bromide. Again, you change the ending to the IDE because you always change the name of that non-metal, okay? And so I would get lead 2 bromide. Again, we can take a look at another example where you have to figure out a multivalent element. Let's take a look at maybe we'll look at tin oxide. All right, so when I take a look at my periodic table, I have tin, and I have probably a couple charges on that, and I know oxygen is O2 minus. Now, I can take a look at my periodic table and say that, okay, well, I have some sort of charge on tin, or because I know that oxygen is 2 minus, I needed 2 oxygens with a 2 minus charge, which means that this has to be a 4 positive charge. But we'll just jump over to our periodic table. In case you didn't follow that math, we have our 2 minus, 2 of them, 4 negative charge. I need a 4 minus, and I only have 1 tin. So I needed a 4 positive, to cancel out those two oxygens. So when I jump over, where is it? There we go. When I jump over to my data booklet, I take a look at tin, and sure enough, I have a 4 positive or a 2 positive charge there. So when I jump back, it means that I was correct to choose my 4 positive charge. Now, again, this was or my 2 positive charge, but that didn't really matter. So when I go to name this, I get tin 4 oxide. And again, because this reduces to our lowest coefficients, we see that I would crisscross my 4 and my 2, but I would cancel out my 4 and divide it by 2 to get a 2, and I'd cancel out my 2 by dividing my 2 by 2, which is 1. So that's how I go in reverse for those guys. If we take a look at something like, let's take a look at one more example. Okay, if I take a look at this example, I know that these charges down, or these numbers here telling me how many ions that I have to deal with, came from my charge on my ion. So this 3, if I go in reverse, it actually came from the iron. So this was iron 3 positive. And because this whole entity is in brackets, I know that that whole thing must be a polyatomic ion. So because I know that this is a polyatomic ion, I can look on my polyatomic ion chart there, and I'll see that this is sulfate. And sulfate has an SO4 2 minus charge. So when I go to name this, again, I would name this because iron has more than one charge. And if you are not sure of that, that's just something that I know off the top of my head. But if you are not sure of that, make sure you jump back to your periodic table to check if there is more than one charge or if this is a multivalent element, because that will help you out when you're writing these. Okay, again, because this is multivalent, I do need to indicate that it is iron 3 sulfate. Now, please note in my 3 examples on this right-hand side, they were all examples that involved a multivalent element. However, you may not have a multivalent element, so you may not need to indicate the charge in brackets. So that example would be something like, let's go with sodium hydroxide, NaOH. So if I have NaOH, I'm going to deal with my sodium, which is my Na positive, and my OH, which is OH minus. Again, if I have 2 non-metals in there, I expect that this is a polyatomic ion. So if this is a polyatomic ion, I notice it's hydroxide, where I would get sodium hydroxide. I don't need to indicate the charge because there is only one charge on our sodium. So if we go over to naming molecular compounds, our naming of molecular compounds is a little bit different than our naming of ionic compounds. Okay, we deal with some prefixes, and we have to be sure that we are only dealing with compounds with 2 nonmetals. So if we take a look at one of those examples, or a few of those examples, we'll do it the same way here. Let's start with carbon dioxide. All right, if we start with carbon dioxide, I know that I find molecular compounds, by the way, to be a little bit easier than ionic compounds. There's less figuring out to do. We always start with our prefixes. Now remember, our prefixes are, jot those down on the side here, mono for one, di, tri, tetra, penta, hexa, hepta, octa, and nona. So those are our prefixes 1 through 9. And essentially our naming says that unless it's the first element and that first element has only one, like this example, I wouldn't say monocarbon dioxide, I just need to say carbon dioxide. So what that means is that I have one carbon and my di tells me I have 2 oxides. So that means that, and this means 1, no prefix in front of my first element means 1, which means I have 1 carbon and 2 oxides or dioxides. If we take a look at another example, I can have, say, something like sulfur trioxide. Again, my no prefix in front of my sulfur tells me that it's 1, and my tri tells me that there's 3 oxides. So it's sulfur with 3 oxides. Okay, so if I continue through, I can have other examples like dinitrogen, tetraoxide. Okay, again, because this case I have a prefix other than 1 on my first element, I need to indicate what that is. Okay, and then the tetra indicates for my second element, which is 4. So if I have dinitrogen, 2 nitrogens, tetraoxide, so I have N2O4. So again, these I find it to be a little bit more simple because you are told exactly how many of each element you have. Now again, you have to be careful when you list these and when you write them down so that you have 2 nitrogens, 4 oxygens, and you don't mix up your subscripts there. Okay, if I go in reverse, I can take a look at an example like this. This one, again, my number at the bottom here tells me how many I need of each. So in my first element, I have diphosphorus. And notice in my first element, I never change the ending to an IDE. I only have an IDE ending in my second element listed. So I have diphosphorus pentaoxide. Again, notice I've changed my second element to have an IDE ending. If I have certain elements such as O2, this is by any stretch of what we know is dioxide. However, we have to remember that we have some diatomic elements. So we have oxygen, hydrogen, any of the halogens, things like that. Those are diatomic. We have other polyatomic ions, such as phosphorus, which is P4, or S8, which is sulfur. Okay, I can go through and I have other examples. Let's take a look at so again, because there's just one phosphorus, I don't need to say monophosphorus. I only need to say mono if it's the second element. So I have phosphorus, pentachloride. Squish that in there. Okay, or again, one last example. CO, I have one carbon. I don't need to say monocarbon. I just say carbon. However, on my second element, I do need to include the prefix, so this is carbon monoxide. All right, again, notice the endings. Okay, do not forget your diatomic elements or polyatomic elements, and ensure that you only include mono as a prefix on your second element when you're listing these molecular compounds. Now there is a couple worksheets for you to take a look at and to practice up your naming of ionic and molecular compounds. Your ionic compounds have examples of polyatomic ions as well as multivalent elements, so there should be lots of practice there for you. As well as your molecular compound worksheet will have other common molecular compounds such as methane, okay, which is CH4, and other common polyatomic, other common molecular compounds that you may need to just be familiar with as you go through. All right, that should be everything for identifying and classifying our compounds, either ionic or molecular. Good luck!